Look at your hands. Go ahead, hold them up. Clap them together. What do you feel? You feel the solid impact of one hand hitting the other. They don't pass through each other. Now push your hand down on the table in front of you. It's firm, it's solid, it supports the weight of your arm. This is our everyday reality. Solid objects we can touch. Solid objects we can hold. Solid objects we can lean on. Everything our intuition tells us about the world is built on this simple fact. Matter is solid. It has substance. It keeps you from falling through the floor. It lets us build skyscrapers that reach for the clouds. But what if I told you that this feeling of solidity is an illusion? What if the very atoms that make up your hand and the table are almost entirely empty space? Sounds like science fiction, right? The idea that you are made of nothing, that the chair you're sitting on is a ghost, it defies common sense. Yet this is a fundamental, mind-bending truth discovered by science. The solid world we perceive is built from building blocks as empty as the solar system. This is the great paradox of matter. Let's try a thought experiment. Imagine you could shrink down, past the point of visibility, down to the atomic scale. As you zoom into your hand, the familiar surface would dissolve. You'd be floating in a vast empty void, dotted with incredibly tiny, faraway specks of matter. The substance you thought was there has vanished, replaced by astonishing emptiness. If your hand is mostly nothing and the table is mostly nothing, why don't they pass through each other? Why don't you fall straight through the earth? This puzzled some of the greatest minds in history. It challenges our basic assumptions about reality. The answer isn't simple, but it's fascinating. It takes us from the early days of physics to the strange and wonderful rules of the quantum world. To understand why you can't walk through walls, we must unpack what an atom truly is and explore the invisible forces that govern it. This journey will change the way you see the world, revealing the hidden architecture that makes it seem solid. Our story begins over a century ago, in a laboratory in Manchester, England. A physicist named Ernest Rutherford was trying to understand the structure of the atom. At the time, the prevailing idea was the plum pudding model. Scientists imagined the atom as a sphere of positive charge, with tiny negative electrons scattered throughout it, like plums in a pudding. It was a neat and tidy picture, suggesting that matter was more or less uniformly dense. Rutherford decided to test this model with a clever experiment that would end up changing our understanding of reality forever. He took a radioactive source that fired out tiny, positively charged particles called alpha particles. Think of them as incredibly small bullets. He aimed this stream of particles at a sheet of gold foil that was unbelievably thin, only a few hundred atoms thick. Around the foil, he placed a screen that would light up whenever an alpha particle hit it. According to the plum pudding model, the alpha particles should have passed straight through the gold foil with only minor deflections, like a bullet firing through a thin mist. Most of them did just that. But then something completely unexpected happened. While observing the experiment, Rutherford and his assistants noticed that a few particles, about 1 in every 8,000, were deflected at very large angles. Even more shocking, some of them bounced almost straight back, as if they had hit a solid wall. Rutherford later described his astonishment, saying, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." This single bizarre result could not be explained by the plum pudding model. The atom couldn't be a soft, uniform sphere. This shocking observation forced Rutherford to abandon the old model and propose a radical new one. He concluded that the atom must be mostly empty space. All of its positive charge and almost all of its mass had to be concentrated in an incredibly tiny, dense core at the center, which he called the nucleus. The lightweight electrons, he reasoned, must be orbiting this nucleus from a great distance away. This was the birth of the nuclear model of the atom, a model that painted a picture of a miniature solar system, with a dense central sun and distant orbiting planets. And with it came the profound realization Matter is mostly emptiness. Rutherford's discovery opened a Pandora's box of new questions. If the atom is mostly empty space, then the central mystery becomes even more urgent. The scale of this emptiness is hard to comprehend. If you were to scale up an atom so that its nucleus was the size of a marble, its outermost electrons would be orbiting as far away as the length of a football field. Everything in between would be empty space. Your body, the chair you're on, the planet beneath you, all of it is composed of these ghostly, empty structures. The solidity we feel is not what we think it is. This is the quest we are embarking on today. We'll follow the trail of discovery that began in Rutherford's lab and journey deep into the heart of matter. We will explore the forces at this minuscule scale, forces unlike the everyday pushes and pulls we know. These forces create the illusion of solidity from near total emptiness. They are the invisible glue holding our world together. Understanding them requires stepping into the bizarre realm of quantum mechanics. Our investigation is a story in 3 acts. First, trace the history of the atom, from solid billiard balls to Rutherford's empty planetary model. Next, dive into the invisible forces. Electromagnetism prevents atoms from squishing together. The Pauli exclusion principle, an invisible shield. Finally, how atomic rules build solid materials, the hardness of a diamond, the flexibility of rubber. By the end, you'll know. Why can't you fall through the floor? The answer will deepen your appreciation for the hidden, complex, beautiful reality beneath the surface. The solid world is a grand illusion. We're about to pull back the curtain and see the trick. So, get ready. The universe is about to get stranger and more interesting. Let's begin. Rutherford's planetary model was a monumental leap forward, but it also created a huge problem. The problem lay with the electrons. According to the physics of the 19th century, any accelerating charge must radiate energy, broadcasting it away as light. It wouldn't be a stable planet-like orbit at all, but a death spiral. The atom, as described by Rutherford, should not be stable. It should collapse in on itself almost instantly, in about a trillionth of a second. The universe should have blinked out of existence the moment it was formed. Clearly, this does not happen. The old physics was breaking down at the atomic scale. It was like building a beautiful house that was designed to fall down the moment you finished it. This was a crisis in physics. Something was missing. A new rule, a new principle, was needed to save the atom from itself. Before we dive into the quantum world that saves the atom from collapsing, let's address the first part of our main question. Why can't your hand pass through a table? The simplest answer, and the first line of defense, is electricity. At the heart of it is a simple rule. Like charges repel, opposite charges attract. So when you push your hand down on a table, what's really happening is that the electron clouds of the atoms in your skin are getting very close to the electron clouds of the atoms in the wood. And since all electrons carry a negative charge, they furiously repel each other. This repulsion is incredibly powerful. It's this electromagnetic repulsion that you feel as the solidness of the table. You are not actually touching the table. What you are feeling is a force field. So, in a very real sense, you have never truly touched anything in your entire life. When you sit in a chair, you are actually levitating a tiny, imperceptible distance above it, suspended by a cushion of electromagnetic repulsion. In 1913, a young Danish physicist named Niels Bohr came up with a radical solution. He took a bold leap. The old rules of physics simply do not apply inside an atom. Instead, they are restricted to specific, fixed orbits, energy levels. Bohr's idea was like saying you can stand on a ladder, but only on the rungs. If an electron stayed in an allowed orbit, it would not radiate energy. It would not spiral into the nucleus. It could stay there forever, perfectly stable. Electrons could jump between levels. Jumping down released a specific packet, a quantum of light. but it was only a halfway house. The final answer demanded a bigger leap, a rethinking of what an electron even is. The electron was not a tiny planet after all. Think of the electron as a wave of probability. Its location is smeared out in space. Instead of a neat orbit, we have a fuzzy region where the electron is likely to be found. This region is called an orbital, or more evocatively, an electron cloud. The electron isn't a planet, it's a standing wave of probability. Much like a guitar string resonating with a specific note. The lowest note corresponds to the ground state. It cannot play a lower note that would cause it to crash into the center. This waviness and uncertainty give the atom its size and stability. The atom's emptiness is not empty. It's filled with the ghostly presence of probability clouds, the fabric of quantum reality. But there's one more crucial piece of the puzzle. It was discovered by the Austrian physicist Wolfgang Pauli. It's called the Pauli exclusion principle. It says no two electrons in an atom can be in the exact same quantum state. Think of it as an electron's unique address, like a labeled seat. Once a quantum state is filled by an electron, no other electron is allowed to enter. That seat is taken. This is why electrons don't all pile into the lowest energy level. The first energy level has room for 2 electrons. Once that level is full, the next electron is excluded. It must occupy the next available energy level. This is how the beautiful, shell-like structure of atoms is built up, level by level, electron by electron. Without the Pauli exclusion principle, chemistry would be impossibly boring. There would be no periodic table, no complex molecules, no life. As you try to squeeze the electron clouds of one atom into the space already occupied by the electron clouds of another. The Pauli exclusion principle creates an ultimate resistance, a kind of quantum stiffness. The resistance doesn't just get bigger as you push, it becomes effectively infinite. An atom's electrons simply cannot and will not be compressed into the space occupied by another atom's electrons. This is the ultimate reason for solidity. It turns the fuzzy, ghostly probability clouds of electrons into impenetrable, rigid spheres when you try to push them together. Matter feels solid not because it's full of stuff, but because it's full of rules. The atom is mostly empty, but that emptiness is governed by laws so strict that they make the void as solid as a wall of diamond. To understand the solidity of a block of steel, we must now move beyond single atoms and ask a new question: how do atoms hold hands? This process of sharing or transferring electrons is what we call a chemical bond. In diamond, each carbon links to 4 others in a perfect 3D tetrahedral lattice. That makes an incredibly rigid, interconnected network. To scratch diamond, you must break those covalent bonds. Metals have a completely different strategy. Each atom donates 1 or 2 valence electrons to the whole community. Picture an orderly lattice of positive metal ions, sitting in a mobile sea of shared electrons. When you bend a paperclip, rows of positive ions slide past each other. The electron sea flows with them, adjusting and keeping the metal intact. In many solid materials, atoms don't clump randomly. They arrange into highly ordered, repeating patterns called crystal lattices. The specific geometry of the lattice profoundly affects material properties. In diamond, a tetrahedral network makes it incredibly hard. In graphite, 2D sheets makes it soft. When you push on a crystalline solid, you push against the entire interconnected framework. The force you apply is distributed through the lattice, resisted by every bond. Hardness is resistance to breaking bonds. Elasticity is the ability of bonds to stretch and snap back. Brittleness is very strong but rigid. All these macroscopic properties echo the quantum world of electron bonds and crystal structures. For most of history, this entire discussion would have been theoretical, but no one could actually see an atom. Then, in the 1980s, a revolutionary tool arrived: the atomic force microscope. It works like a tiny record player. As the tip scans across, tiny forces between tip atoms and surface atoms make the cantilever bend or vibrate. A laser bounces off the back of the cantilever onto a detector. A computer reconstructs a 3D topographic map of the surface. The result: a direct image of individual atoms in their crystal lattice. A stunning confirmation of a century of theory. The AFM doesn't just see atoms, it feels them. Pushing your hand on a table, that same principle, extremely sensitive. They have made the atomic world tangible. We have seen that the feeling of solidity is not a property of one thing, but the result of a beautiful, multi-layered system of rules and interactions. It's a symphony of collective behavior. It's like watching a flock of birds. A single bird has simple behaviors, but when thousands of them fly together, they create complex, beautiful patterns that are a property of the flock, not the individual. Solidity is a property of the flock of atoms. So, the next time you clap your hands or knock on a wooden table, take a moment to appreciate what is really happening. You are not touching a solid object. You are experiencing a symphony of physics. You are feeling the force fields of countless electron clouds. You are pressing against the unbreakable law of the Pauli exclusion principle. You are testing the collective strength of trillions of chemical bonds, all of which are built from atoms that are themselves 99.999% empty space. The solid world is a grand, beautiful, and robust quantum illusion. This new intuition doesn't mean the world is any less real, but its solidity is an emergent property. It emerges from the collective behavior of trillions of atoms, all obeying a few fundamental quantum rules. Science allows us to look behind the interface, to see the source code of the universe. It pushes us to question our most basic assumptions. It forces us to be humble about what we think we know. The fact that we can even begin to understand these bizarre, counterintuitive rules is a testament to the power of human curiosity, experimentation, and reason. We live inside a magnificent quantum magic show, and knowing how the trick is done doesn't ruin the magic. In fact, it makes it even more wonderful. The wall feels solid not despite being empty, but because of the rules that govern that emptiness. You are held together and held up by the strange and beautiful logic of the quantum world. The next time you feel the solid ground beneath your feet, smile. You know the secret. You're standing on a ghost, held up by a paradox.